Welcome everybody. You are signed on to the Rotronic Instrument Corporation webinar called Humidity, How to Make a Better Measurement. These Rotronic humidity webinars are designed to help you make a more reliable, repeatable, and accurate measurement of humidity. And that's the whole topic of this webinar, how to make a better measurement. And as we always say, the first step to making a better measurement is to understand that parameter that you wish to measure. Everyone who registered for this webinar will receive a copy of the slides and a link to the recorded webinar. We send this out two ways. The first is via email. We send out an email within about 24 hours of this live broadcast, and then we'll also post the slides and the recording link on the Rotronic website. Everyone is in listen-only mode. That means you cannot speak to us directly via your computer or your phone, but we do want you to interact. And the way to interact with us during the webinar is look for on your control panel, look for the questions pane, and that's where you can not only type questions, but you can also type comments. As we go through the webinar and a question comes to mind, go ahead and type it in at any time. We'll have 2 Q&A sessions during this webinar where we'll queue up the questions and take them one at a time and answer as many as we can. So yes, we do encourage you to ask questions. That's the fun of a live broadcast. This webinar is presented and produced by Rotronic Instrument Corporation. If you don't know Rotronic, Rotronic manufactures precision measurement instruments for humidity, of course, dew point, carbon dioxide, temperature, water activity, and a few others, in addition to a new state-of-the-art leading-edge environmental monitoring system. Now, we don't talk about these products. We don't pitch the products during these webinars because it's educational, but naturally, if you do have questions about Rotronic instruments or the Rotronic monitoring system, please reach out. Give us a call or find your sales contact on the Rotronic website. It's rotronic-usa.com. Speaking today, my name is Bruce McDuffie. I'm with the Rotronic Marketing Department. I've also been in the humidity measurement business for about the past 10 years. I've got strong application knowledge from being a field sales rep, and I've taught many humidity measurement webinars and live seminars over the past 10 years. Michael Botskis is your co-presenter today. Michael works in the metrology department for Rotronic, and he specializes in relative humidity and temperature measurement. Michael's been involved in manufacturing and calibration of humidity and temperature for about the past 19 years. Welcome, Michael.
Thanks, Bruce. It's great to be here today.
It's great to have you on as an expert on the webinar. And with that, I'm going to turn it over to Michael to go through our agenda and takeaways that we're shooting for today.
Thanks, Bruce. So, as mentioned, today's webinar is all about how to make a better measurement. So we're going to go over topics that will help you understand what it is you're measuring and what different what different environmental effects can affect your measurement. We're going to start off going into some of the theory and some of the science behind humidity so we get a better idea of how different parameters will affect our measurements. The key parameters that we will talk about are the temperature effect and the pressure effect, and we'll see what do these do to the relative humidity we're trying to measure and how do they affect the instruments themselves. We're also going to look at a couple different sensing technologies. We'll look a little bit at what they actually measure versus what they calculate and report. The key takeaways for today is the most basic one is to try to give people more knowledge about what it is they are measuring and how all the environmental factors come into effect for that measurement. We're going to talk a lot about temperature, and this is something we're going to bring up a lot today, the temperature effect. How does temperature affect our relative humidity measurements? We'll also look a little bit at pressure and how it affects this. And hopefully we can give some ideas of how to match up the different technologies to different applications and also really emphasize what do these technologies measure versus what are they calculating and what impact does that have on how you're trying to report your data. But to start off, I believe Bruce has a couple polls for us just to get to know everyone a little bit better.
Yeah, just a couple of quick polls for the audience. It's, interesting, I think, to know who else is out there. It may seem like you're the only one on the webinar, but we've got a couple of hundred people signed on this morning. So let's see who's out there. First question I'll ask is, what is your industry? Just choose either one of those 4 industries that we put up there, or if yours is other, go ahead and type in the question pane. Get some practice there. Type in the question pane what industry you are working in. But that other is taken right off, Michael.
It sure is.
There's a few folks typing in. Jay is with pharma, Kyle's in testing, Bruce is in woodworking, David in automotive, Joel in calibration, Nathan with NOAA, Zach metrology, Sam in aerospace. Wow, it's a lot of them. The problem, folks, is I only get 5. I can only put 5 choices in the poll. Other than that, we've got a good section from pharma. We'll give it a couple more seconds here. Some HVAC and food production. I'll go ahead and share the results. We can take a look. You can see that other is big. We've got, let's see, we've got guitar manufacturing. That's a new one, but I can see how humidity is important for that. Utilities. Okay, thanks everyone for sharing that information. And the second question I have for you is, make sure I get to the right place. What is your role? What's your role today? Or I guess all days maybe. Are you the boss, facility manager, lab manager, technician, or other? And again, if you want to share what other is, we're happy to take a look at that. We've got engineer. Jay's an engineer. Kevin is in K through 12 education facility. A few other engineers. We should probably add that one on there.
Yeah, our other is taking off again.
Yeah. Got a sales consultant. That's okay. Salespeople are welcome to these. No, I love salespeople. Indoor air quality validation. Okay, good. Thanks, folks. And I'll go ahead and give it a couple more seconds. Close the poll. I know you want to hear the content here. Show folks the results. You can see, again, we've got a few bosses out there, facility managers, a good mix. It's always good to have a good mix. That helps with the questions that come in. Okay, let's go ahead and get into the presentation. And we'll start off with the science of relative humidity because, again, it's important to understand the parameter you wish to measure. And to do that, we need to understand the science. And this is not in-depth. If you want an in-depth discussion about humidity science, we did a couple of webinars that are in the on-demand section. For one was relative humidity and dew point, the basics, and one was theories and definitions. Check those out too. Before I do get into it, I want to point out in the handout section of the control panel, look, open that up if it's not open, and you can download our 26-page Rotronic Humidity Theory ebook. It's an excellent add-on for this, and usually we make you fill out a form, but through the webinar you can download it directly. It's all yours, no charge. Please, I encourage you to get that handout. And again, it's in the handout section of your control panel. Let's start out talking about Dalton's law of partial pressures. John Dalton was a physicist back in the late 1700s, and he invented many things. And one of the things he did develop was and prove was Dalton's law of partial pressures. And what it states is that the total pressure of a gas mixture is equal to the sum of the partial pressures of each of the gas components. For example, the air you're breathing, if you're at sea level, the pressure is probably about 1,013 millibars, and the air is made up of several gases: nitrogen, oxygen, carbon dioxide, a few other trace gases, and water vapor. Water vapor is one of the gases that we live around. So water vapor, as one of the gases, contributes a portion of the total pressure. And that's why we can quantify the amount of water vapor present with a pressure parameter. Another important part of the science to understand is the term saturation vapor pressure. And this is extremely important because it does not change with pressure. It does not change with differences in the amount of water vapor present. It does change with temperature. And this is a key theme we'll be sharing throughout, that when you're measuring relative humidity, as your temperature changes, your saturation vapor pressure changes, and that causes a fluctuation in your relative humidity measurement. So know that as your temperature changes, your saturation vapor pressure changes. And if we look at the formula for relative humidity, partial pressure divided by saturation vapor pressure, it's like any fraction. When the denominator changes, varies, even if the numerator stays the same, you're going to get a variation. And that's one of the big problems people have with measuring relative humidity, because the temperature is not uniform. Relative humidity is relative. That's the key. Many times people ask about or talk about humidity, they really mean relative humidity. And the reason it's relative is because it's relative to the temperature and the potential for air to hold water vapor. For example, on the right-hand side over here, if we have air at 30 degrees C and we have water vapor present that's quantified at 12.3 hectopascal, we divide 12.3 by 42.4 and we get 28%. So the 28% says that that's the relative to the total amount that's possible. If we look here on the left-hand side and we were to cool that air down to 10 degrees C, now at 10 degrees C, that air can only hold 12.3 hectopascal. So we're using up 100% of the capacity. And that's where the relative comes in relative humidity. The key point here, and we're going to talk more about it, Michael, is that temperature is important because that saturation vapor pressure varies with temperature. And with that, Michael, let's talk even more about this temperature effect.
Well, I think we actually had one quiz before we went into the temperature effect.
Did we have a quiz? Oh, that's right, we did. Thanks for reminding me. Folks, let's see if you're awake and paying attention. The question is, the relative in relative humidity is it because the property is relative to partial pressure? Is it because the property is relative to the number of people in the room? Is it because the property is relative to saturation vapor pressure? Is it relative because the property is relative to pressure? Or the property is relative to room size? I can see folks are thinking about this one, which is good. We want you to think. Give it a few more seconds. I can hear the wheels grinding all the way from here in Boulder, Colorado. Michael, can you hear them up there in Vancouver?
I definitely can. My own are going, okay, what is it? What is it?
Okay. Looks like folks have voted. We'll go ahead and give you a couple more seconds. 3, 2, 1. Closing the poll. And I'll share the results. The correct answer is that the relative in relative humidity is there because the property is relative to that saturation vapor pressure, that curve we just showed. And of course, one could argue a couple of these other ones, like the people in the room, but the best answer is the third one. Okay, I'll go ahead and hide this, and back to you now, Michael. Let's go ahead and talk more about it. Okay.
Okay, so we're going to spend a bit of time here on the temperature effect because the temperature effect is probably one of the biggest impacts that most of us will see when we're measuring relative humidity. So for a space, a room, or a chamber to have a uniform relative humidity, one of the conditions that must be present is a uniform temperature. Just going back to that saturation vapor pressure curve, we can see here that it is only dependent on temperature. So if the temperature in the space has any gradients in it, that means that the saturation vapor pressure is changing over that space, which would cause the relative humidity to change itself, because it changes one of the parameters in our formula for relative humidity. So we have to understand that our relative humidity is dependent on the temperature in our space. So our relative humidity sensors that are actually measuring relative humidity, they are sensitive to this temperature, and they actually have a second order effect in that they have a temperature sensitivity beyond just the relative humidity and the saturation vapor pressure effects. Most often though, that part is taken up in the electronics of the sensing system itself. We also have to keep in mind that our measurement probe must be at a uniform temperature. If there's any gradients along that probe, that can potentially create a microenvironment at our sensor where we've got an incorrect temperature. We also want to make sure that our measurement point is representative. When we're in a large space like a warehouse, we want to make sure we're taking our measurements somewhere where we've got our average temperature and avoid any hot and cold spots. In Bruce's example earlier on, we saw the effect of a large temperature change, which hopefully when we're measuring inside a room or a chamber, we're not going to see 10 degrees C swings, but it is very possible for us to see a 1 degree C change. So we want to just take a look at an example here and just get a better idea of the impact that a 1 degree C change can have on our measurement. So in this case, we've got a chamber here set to 40 degrees C and about 55% relative humidity, 54.2 to be specific for this example. And so we know what our partial pressure of water vapor is, and we know what our saturation vapor pressure is. And all we're going to do here is change the temperature. The water content in this chamber is not being changed at all, and we can see that by our partial pressure not changing in any of these examples. But as we change, we drop the temperature by 1 degree C. We can see a fairly significant change in the saturation vapor pressure. So the air is now able to hold less water, and this leads to a 3% relative humidity increase, because that air can hold less water just with a 1 degree C change. It affects our relative humidity to 3%. If we went in the opposite direction and raised the temperature by 1 degree, now that air can hold more water vapor. So our saturation vapor pressure increases and our relative humidity decreases. One thing to keep in mind here, you'll notice that the relative humidity has not decreased by 3%, but it's only 2.8%. And this, if you go back to the saturation vapor pressure curve, you'll notice it's not a straight line. There's nothing linear about relative humidity. It is on a curve, so the temperature effect will change depending on what temperature you're at and how much the temperature change is. So a couple things to keep in mind when we're dealing with relative humidity measurements. One example here that I've run into many times with customers and users of humidity instruments, they'll want to measure something in a chamber and they'll have a probe to go into that chamber. But they still see an error in their readings. They're not getting what they expect based on the set points. So in this example, we've got a temperature or a environmental chamber set to 40 degrees C, 50% RH. We've got a probe going into it, and the bulk of that probe is sitting in our ambient lab condition, 23 degrees C, maybe 30% relative humidity. And we're seeing a significant difference between our temperature and humidity values between the probe and what we expect based on the set point. And the question is, what's causing this? Well, this is a great example of a temperature gradient along the probe. What we're seeing in this specific example is actually that we don't have the probe immersed enough in the chamber, and we're actually seeing a a temperature gradient along the stem of the probe, and that's causing the temperature sensor and the humidity sensor to be cooler than what's actually in the chamber. And this is giving us our 3% RH error, because our temperature on that probe is reading about 1 degree lower than what that chamber set point is. So here's a really quick and easy example of how we can get incorrect relative humidity readings just from the setup of our instruments. So it's important that we take this into account and we ensure that our probes have a uniform temperature to deal with. So there's several other causes of temperature effects in our environments. Us as users are often one of those things that can cause a temperature effect, either by holding the probe in our hand. If we're measuring a room that's at 23 in our hand's going to be warmer than that typically. So we could end up heating the whole probe up depending on how big it is, which creates a microenvironment, and now we're not measuring what we want for the room. Our body's heat generators. If we're too close to the probe, we can be changing the temperature. And we're also, when we breathe, we're breathing out very moist gas. So that will have a direct relative humidity effect on the sensor, even beyond the temperature effect. We want to make sure that the probe is not colder or warmer than ambient air. We see the example of our bodies potentially causing that effect. But it can also come from taking the probe from one environment to another. So either putting a probe into a chamber right away and not letting it come to equilibrium, or potentially we're a field technician and our probe's been in a hot car or a cold car depending on the season, and we're going into an environment to take a measurement. It's especially important for us to take into consideration putting a colder probe into a warmer, humid environment, because in that case we'd actually get condensation on our probes. So they would read 100% until the sensor itself dries out. In addition to this, we need to watch out for hot and cold spots in our room. So we don't want to put our sensors right next to the cooling fan for a piece of equipment or in the direct airflow of an HVAC system, because both of those will give us artificially high or low readings if we're trying to measure the overall ambient conditions in our room. And I believe now Bruce has another quiz for us on the temperature effect.
Yes. Thanks, Michael. And this one, we want to keep everybody engaged here. And the question is, you should see it on your screen here in a second. True or false? A small difference in temperature does not really matter in RH measurement. A small difference in temperature does not really matter in RH measurement. True or false? This is related to what Michael just went over. And this could be actually in itself a source of error in measuring humidity or a problem with reliability. It's a very fine point. Give it a few more seconds. Looks like everyone's voted who wants to. I'll close the poll and share the results. And 95% got that correct. The answer is false. Even a small difference in temperature variation, say between the probe and the environment, can make a significant difference. And with that, we'll go ahead and I'll talk about pressure differences. So what about pressure when it comes to measuring humidity or relative humidity? Relative humidity is not affected, the measurement is not affected unless the pressure varies in the same airstream. So what I mean is if you take a relative humidity sensor or an instrument, same sensor, same instrument, you measure in one pressure, you're going to be accurate, of course, to the spec of the instrument. You take that same probe, sensor, and instrument and you measure in a different pressure, you're going to have an accurate result. But, for example, if say you have an airstream and you have a measurement, a sensor at one point of that airstream that's giving you relative humidity. But what you need is to know the relative humidity at a different point in the airstream that maybe has a different pressure. That's when you're going to have that's when pressure matters, because there's two different pressures, but you're only measuring at one point. Just be aware that that could cause high errors. Other things to know about pressure: dew point is affected by pressure, and you have to make sure when you have an instrument that has, say, for example, a relative humidity sensor and a temperature sensor, and you're measuring at different pressures, that the conversion does matter, or the conversion pressure matters with the conversion. Dew point and pressure, this is the one that's going to matter the most. If you're measuring dew point, you have to be aware that it does change quite a bit with pressure variations. If you're in, for example, a compressor system, or a compressed air system rather, as pressure increases, the dew point temperature will also increase. And if you continue to increase pressure in some air, eventually you would reach saturation and you would get condensation just from that pressure increase. As pressure decreases, your dew point temperature will go down. You're going to get a bit drier. And be aware of pressure differences between the point of interest and the point of measure. For example, let's say you've got a compressed air system. You take a measurement in the line at pressure, but you draw a sample off of the compressed air system. You draw off the sample and you measure that same air at ambient pressure. The dew point is going to be very significantly lower than what it is in the compressed system. So you have to make a correction. You need to know that you're not having a true dew point that's measured in the compressed air. So pressure has to be even between dew point, point of interest, and the measurement. The other thing I mentioned earlier was about the different parameters. So pressure does not affect relative humidity unless, again, you have differences between the point of measure and the point of interest. Dew point, yes, pressure changes in dew point will change your measurement significantly. Wet bulb temperature doesn't matter because we're measuring temperatures. Mixing ratio is an absolute measure of how much water vapor is present. ppm, parts per million, is also a measure of how much water vapor is present. These are typically calculated. So for example, if you have a relative humidity sensor, a temperature sensor, and a pressure input to the instrument, you'll calculate mixing ratio. And just be aware that, for example, when you buy an instrument, a relative humidity instrument, typically there is a pressure input, a pressure setting in the instrument, but it's usually at sea level. So if I go to New York, say I go to New York City and I have my brand new instrument, I take a measurement and I see a mixing ratio, it's going to be accurate. If I take that same instrument to Denver, where we're at 5,200 feet, and I take the same measurement, my mixing ratio is going to be wrong until I change that pressure input. So know what your sensor is measuring, and that's what we'll be talking about here in the next section. But in the meantime, we have another quiz. Yes, we're going to have quizzes after each section. This should be showing up on your screen here in a second. When pressure increases, dew point temperature stays the same, goes down, goes up, or you don't know because you were doing email. When pressure...
Hopefully not too much email.
What's that, Michael?
Hopefully not too much email.
It's hard. You got to keep that email down. When pressure increases, dew point temperature stays the same, goes down, goes up, or you don't know. Give it a few more seconds. Folks are still pondering the question. All right, we've got about everybody who voted who wants to. Not voted, but chose an answer. I'll go ahead and close the poll, the quiz, share the results. Correct answer, 70% got the correct answer. when the pressure increases, the dew point temperature does go up. And once again, the rule of thumb is when pressure increases, dew point temperature goes up and it approaches condensation eventually. When you lower the pressure, dew point goes down. So for example, if you take a measurement of the dew point at the dryer in pressure, your dew point down the line, because pressure is going to decrease down the line, it's going to be a little drier. That could be seen as a safety factor, really. Okay, we'll go ahead and hide the poll and going to turn it back. Oh, we have questions and answers. Okay. So Michael, we do have some questions coming in. And here's one that says, this is an interesting question. What happens after the temperature exceeds 100 degrees C? Say in an environment of 400 to 500 degrees temperature range. I think he's asking what happens to the relative humidity based on the formula P over PS.
Well, the formula still stays the same. We can still have water vapor when we've got at above 100 degrees C. We're just not going to have liquid water there unless we end up in a highly pressurized environment. So the formula still stays the same. We're still looking at the ratio of the partial pressure of water vapor in our environment as compared to how much water vapor can be held there.
Okay, thanks. Here's an interesting one too. These guys are coming up with some good questions this time, Michael. Why can saturated salt solutions remain stable regarding RH percent even at different temperatures?
Well, two things on that. If you go and look at the charts that have been published for the relative humidity that saturated salts will generate, they do actually change over temperature. So the saturated salt solution, it will stay fairly close, but many of them will actually change over as the temperature changes. So it's a little bit false that they don't change over temperature because there can be some change. But after that, it comes down to the relationship of the salt with the water vapor and its ability, how it reacts with it. I don't know all the chemical interactions and some of the physics behind that, but it's got to do with the properties of the salt and then the water vapor.
Okay. Good. That's actually all the questions we have in this first section, unless somebody wants to type one in right now. Give it a couple of seconds. Okay. With that, let's go ahead and move on to the next section, technology. Michael, back to you.
Thanks, Bruce. So in this section, we're going to go through a few different sensing technologies and just review what they're measuring versus what they're calculating to try to get a better understanding of what environmental factors we need to take into account when using them. Before I go too far forward, the first one we'll look at is the psychrometer. We've got a picture of a couple of these here. And for those of you that want more information about the different sensing technologies, we do have another webinar on that, but we'll go through these fairly briefly. The psychrometer is essentially two thermometers. There's a dry bulb temperature, which is essentially just the ambient air temperature. And so that's one of the values that gets measured. The other one is called the wet bulb temperature. And the wet bulb temperature, it's a separate thermometer, and it's got a sock or some other fabric on it that is wet. And as water evaporates from it, that causes the temperature of that thermometer to go down. Because as water evaporates, it takes energy for that to happen, which causes the drop in temperature. So if we're using a psychrometer, we're measuring directly dry bulb and wet bulb, and then parameters, the other parameters are calculated. So things like relative humidity is a calculated value. We're not directly measuring relative humidity. So if we look then at an application and some of the considerations that we need to use, in addition to sling psychrometers, which would be a handheld device, These are also used in environmental chambers to control relative humidity. So some of the considerations we need to do is we need to ensure we've got clean water. If we don't have clean water, potentially the evaporation rate from the wet bulb sensor will differ, and that's going to directly affect our calculated relative humidity. The same thing goes for having a constant airflow and sufficient airflow over the sensors. If there's not sufficient airflow, again, the evaporation won't happen as quickly, and we'll see an error in our relative humidity readings. In addition to this, we of course need to remember that there could be temperature gradients within our space, and that will lead to relative humidity gradients. So if we're trying to define what the entire space is, we need to have some understanding of what those temperature gradients are. And of course, with a wet bulb or with a psychrometer, it's constantly evaporating water, so we're constantly adding more moisture into our environment, and that will cause potentially the relative humidity to increase if we've got a very small chamber. Bruce, I'll pass it on to you for capacitive sensing systems.
Okay, capacitive sensors are probably the most common sensor out there used to measure relative humidity and probably humidity in general. The way these work is, obviously, it's a capacitor, and the dielectric of the capacitor is a polymer. And as the relative humidity changes in the environment you're measuring, the property of the dielectric or the polymer changes, and that will change the capacitance. And as the relative humidity increases, typically the capacitance will also increase. Usually when you have a capacitive sensor, you also have a temperature sensor in the same probe. And based on these two measurements, you can calculate the other parameters, wet bulb, dew point, frost point, vapor pressure, and so on. And that's essentially how these capacitive sensors work. Applications, these are again probably the most widely used type of sensor technology. They're used in HVAC, outdoor weather, monitoring systems, process control, and they're probably the most versatile as far as range of measurement and conditions and temperature range as well. There's a few capacitive sensors out there that are actually modified so they can measure trace moisture down to -60 or -70 C dew points. And there's others where the probe is modified where they can measure in condensing environments. So again, very versatile, probably the most common, but as Michael mentioned, the important thing to know that is a capacitive sensor is measuring the property of relative humidity. So this is where temperature comes in. If you know, and you should know, what technology your instrument is using, and its capacitive sensor, make sure you pay attention to those problems, potential problems with temperature variations that Michael talked about in the temperature effects section. And back over to you, Michael, for a chilled mirror.
Thanks, Bruce. So we've got a diagram of a chilled mirror here. And so what it essentially is we've got an airflow going over a mirror that has cooling capabilities on it. And that mirror would get cooled down until the point where dew or frost forms on it. The sensor would sense that dew or frost being formed by shining a light at the mirror and measuring the intensity of the light that's reflected off. As the dew or frost forms, the intensity of light reflected off goes down. So that's how the system knows what the dew point is. So these systems then, by definition, are measuring either dew point or frost point, being the point where we've got that condensation happening. And they'll also typically have a dry bulb temperature or a temperature sensor to measure the ambient air. Occasionally, some of them will also have a pressure sensor on them, which can be very important as well. The calculated values out of these would be the relative humidity, and if you want, the vapor pressure of water. And you'll notice I've also put down that the dew point is calculated. And that is actually the case in certain circumstances. One of the interesting things about water is water does not have to freeze as it goes below 0 degrees C or 32 Fahrenheit. There is a situation known as supercooled water, where water can stay in its liquid form well below the freezing point. It can be still in its liquid form down to about minus 20 degrees Celsius or below. And that causes a problem or a challenge with chilled mirrors in that you need to know, do I have dew on my mirror or do I have frost? Because below 0, the dew point and the frost point are actually different. So that's one of the big challenges that we've got with chilled mirror technologies, and will cause errors in our calculated relative humidity. If a great example that I have for this one is any measurements around 10% relative humidity. This is a case where often a chilled mirror could still have liquid dew on it instead of frost. The dew point and frost point are about minus 10, minus 11 degrees Celsius, but if you don't know which one's there, you'll get about a 1% relative humidity difference. And unless you know what's on your mirror, you can't accurately calculate what your relative humidity is. So when we're looking at the use of these chilled mirrors, typically they're going to be used in a laboratory environment. They're going to be a reference in our calibration systems. There's a few other cases where they might be used, but this is probably one of the key areas that they are used, and it's primarily because they've got very low uncertainties, and they're some of the more accurate, or they can be some of the more accurate instruments for measuring water content in air. We definitely need to consider that any relative humidity value that they report is calculated. That means it's going based on the air temperature, and also it needs to have an idea of what the pressure is. Some of these devices will have a pressure sensor on them. Others will make an assumption about what that pressure is. But if that pressure value is incorrect, our relative humidity value will be incorrect as well. We do need to watch out for temperature and pressure gradients. It's with chilled mirrors that we can potentially have the issues related to pressure differences in our gas stream causing relative humidity changes. So an important thing for us to keep in mind. One of the key things, what is the mirror measuring? Are we measuring dew point or frost point? That has a huge impact on our calculated values. Some of these chilled mirrors actually use a sample tube coming from the environment that we're trying to measure to bring that gas to the chilled mirror head itself. And if we're taking a sample gas from a warm, humid environment and we're running that sample tube through a colder environment, we have to make sure that we don't get condensation in the sample tube, because then we'd actually be pulling moisture out of the gas stream and we'd get an incorrect dew or frost point reading. So those are some of the considerations that we need to do just to make sure that we're getting a good measurement when we're using a chilled mirror. Now I will pass it back to Bruce then for our last example on the metal oxide sensors. Bruce.
And also, folks, go ahead and type in your questions, and we'll be having another Q&A session here after the technology section. So if you have questions about any section of the webinar, go ahead and type them in and we'll do our best to get to all of them. Metal oxide. These are, the most common of this type is the aluminum oxide sensor. And the way these work is you've got an aluminum base, and then the aluminum is anodized, so you've got a porous layer, and then you put a thin layer of gold over that anodized aluminum. So you essentially have a capacitor, again. And then as the amount of water vapor or the partial pressure of water vapor changes, then the actual concentration of molecules, water molecules, changes, and these molecules adsorb onto the anodized aluminum. And as they adsorb onto the aluminum, then the conductivity changes, and as the conductivity changes, we measure the impedance, and that's what we get to determine the actual vapor pressure, or partial pressure if you will, of the water vapor. And typically these also have a separate temperature sensor that is installed inside in the probe. So based on the vapor pressure that's measured, so these are measuring an absolute measurement, the amount of water vapor present, and the temperature sensor, then you calculate the other parameters. You calculate relative humidity, wet bulb, dew point, frost point, and other parameters. That's essentially how these work. You do need to have pressure and temperature for the conversions. And these sensors are very good for trace moisture. If you've got a very dry, very clean system you're measuring, these work very well. For example, compressed air, say you have a dryer on a compressed air system, it maintains minus 100 degrees C dew point, and you have good filtration, and it's not oil, oil, there's no oil in the air, these would work. Dry nitrogen would also work. But anytime your air is not nice and clean and dry, chances are, for example, if you get condensation in the compressed air system, or the system where you're measuring gets on these sensors, the calibration goes very fast. And then they have to be sent in for a recalibration, which is usually an expensive and long process. If the air is not clean, for example, if you've got compressed air that uses oil for cooling, then that oil can get on the sensor, it can cause a problem. So you have to have, that's the type of applications that you can use them in. If you want more information about, again, as Michael mentioned, about these technologies, and we did a whole webinar on pros and cons of measurement technologies, you can find those in the Academy section on the Rotronic website. And with that, we have another quiz about sensor technology, and then we'll go into the Q&A session. Okay, I'll give it a second to show up here. Okay, what would be your best choice sensor if you needed precise dew point measurement? What would be your best choice? And I know this is a bit simplified. There's other factors to consider, but see what you think about first hunch on what would be your best choice based on what we just presented for precise dew point measurement. Give it a few seconds. The votes are coming in and the questions are coming in. Good. Thanks for those questions, folks. And we're going to have about probably a little over 10 minutes for questions and answers. So now's your chance. See if you can put Michael on the spot. All right. Looks like we'll give it a few more seconds. Some different opinions on this one, Michael. I suppose that one could argue for different ones. I'll go ahead and close the poll, share the results. And the answer we were looking for was the chilled mirror. If you need precise dew point measurement, chilled mirror is going to be your best choice.
Capacitive sensors are also tuned sometimes for that. There's one specifically for dew point, or when, I guess when we're talking about trace moisture, is probably when we'd use dew point rather than relative humidity as our parameter. So that one is also a good second choice. Okay. As well.
And again, there's other factors. And we actually also did another webinar, now that I think about it, on how to choose the right technology. And that's also in the archive on the website. We go through in detail steps, things, I think it's 10 steps or 11 steps, things you should look at in choosing the right instrument, which includes the technology. Okay, that's good. Thanks everyone for participating in those questions and polls and quizzes. And let's go ahead and do the summary, Michael, and then we'll go into the Q&A.
Sure. So a few takeaways. Hopefully we've helped give you a bit more knowledge about humidity and how temperature and pressure will affect relative humidity, both in a space and as well as how the instrument measuring will be affected as well. Are we actually measuring our relative humidity, or are we calculating relative humidity based on some other parameters. So temperature and pressure errors will affect both of those systems, whether it's a gradient in our room will affect the actual relative humidity, or potentially temperature or pressure errors in our instrument itself will affect our calculated values of relative humidity. So it's good to know about that, know temperature will affect our measurements overall, and also hopefully you've picked up now that sensors are operating in different ways, and what is being measured versus what is being calculated can be important in choosing the best technology for your application. And based on that, hopefully now we can go into some questions. See what we got.
Yeah, we do have some questions, excuse me, coming in, Michael. Here's a quick one that Patrice had about the wet bulb, dry bulb. She says, what do you mean by clean water?
Typically, you want to have something clean. So distilled water or deionized water would be good examples of that. What you want to avoid is anything that might have any salts in it. So if you've got water softening systems in your water supply, for example, that could leave some salts in the water itself, and that potentially is you've almost created it's not quite a saturated salt solution, but you're going to affect how well that water can evaporate. So distilled or deionized water would be ideal to use for a psychrometer.
Okay, thanks. Here's one interesting question. Do bacteria levels ever factored in? And then he said, I do water restoration.
I don't know specifically for bacteria. I'd have to look into that more. But I think as far as them being a contaminant, potentially they can affect the measurements, especially if they're building up on the sensors. When anything builds up on the sensor, especially a capacitive sensor or any of the other ones, potentially you've got something that's impacting your measurement. On a chilled mirror, if you've got a large buildup on the mirror, that's going to look the same as dew or frost to the light sensor. On a capacitive sensor, it could slow down the response time, or the bacteria may actually bring more moisture to the sensor, making it seem like the relative humidity is artificially high. So in both cases, there's a potential effect that could be seen.
Here's a question from Mike. He says, if you were to measure the relative humidity in a chamber where pressure can change due to a vacuum, what would be the best way to do that? Should a small sample of air be taken into an isolation chamber?
Now, I'm assuming here that you're interested in relative humidity. And if that's the case, I would use a capacitive sensor to do that, because the capacitive sensor, it senses actual relative humidity. So its value will change based on relative humidity, and it won't care if you've got a vacuum that's changing. Now, potentially in that environment where you've got pressure changes, I'm assuming it's a closed container, so you will actually see relative humidity changes as that pressure changes, as long as the composition of the air is not changing, or whatever is in that. I guess you might not have air in the vacuum chamber, but as long as the composition in there is not changing, as the pressure changes, the relative humidity will change with that by Dalton's law.
Here's one from Joe. When making measurements using a chilled mirror across several points to verify system accuracy, is it better to start at the lowest measurement, for example, minus 65 degree frost point, and increase to the highest measurement, say 10 degree C dew point?
In those cases, one of the things to remember is all materials will absorb water, and they'll absorb it much faster than they'll release it. So when you're taking measurements with a chilled mirror over that range, or really with any instrument, it's good to start at your dry point, and you need to give your system, especially if you're trying to get down to minus 65 C, you need to give your total system enough time to dry out. There will be water molecules coming out of the materials in the system for potentially a long time. So you need to give the system enough time for all of that moisture to come out of it and then take your measurement. So it's good to start at your driest point, let the system dry out, and then move up in your dew point or frost point values from there. So start dry and then go to wet. That will be the fastest way of making accurate measurements.
Here's a follow-up question to the discussion about higher temperatures above 100 degrees C. It's from Guo. I hope I pronounced that correctly. Let's see. There is a Q&A in the question in the first about temperature above the boiling temp, 100 degrees C. The formula is still valid, but what's the relative humidity? Whether the sensor could still measure the moisture humidity. So in other words, I think above 100 degrees C, how does the sensor work to measure relative humidity above that?
Talking about capacitive sensors, even though there's no liquid water, there is water particles in that space, and those water particles will get into the sensor itself. They're not in liquid form per se, but they're embedded in that polymer, and that will still cause the capacitive sensor to change its overall capacitance. So it's still measuring the relative humidity, and it's just by the dielectric change caused by the particles within the polymer itself. So it's still operating. The capacitive sensors, some of them will operate up to about 200 degrees C, at which point the limitation is actually the materials, not the theory of measurement in that method.
Okay. I think, is it true, Michael, that and I believe this is true, the partial pressure is going to max out at 100 degrees C, but the saturation vapor pressure theoretically can still go up?
That's correct, with the caveat that is in sort of our sea level type pressure.
Okay.
The saturation vapor pressure curve does continue to go up, that's correct, and you just won't ever come close to hitting that saturation point unless you're increasing the overall pressure.
Increase the pressure, exactly.
Yeah.
Thanks. Got time for a couple more questions. Can you explain the difference between mixing ratio and dew point? Both, and then Nathan says, both are absolute measurements of water in the air. Why is one affected by pressure and the other is not?
Okay. Well, dew point, it isn't really an absolute measure of the water content in the air, because it can change with pressure. So the dew point is telling us when will the moisture in our space condense. At what temperature will it condense? The mixing ratio is a ratio of the mass of the water vapor to the mass of the other gases in our space. So that one, you're getting down to the level of essentially counting particles, or the mass of particles. So that one is truly absolute. It's not dependent on temperature or pressure, whereas dew point is actually dependent on pressure.
Okay, that's about all the time we have, folks, for questions. I'm sorry if we didn't get to your question. There's still some good ones in the queue, Michael. We'll make sure we get to you via email with your questions, or feel free to reach out again directly. Just to wrap up, check out the Humidity Academy. It's on the Rotronic website. You can see the URL there. There's psychrometric charts, technical notes. There's an online humidity calculator, other application notes, and the whole archive of past webinars. Next webinar will be about calibration of humidity instruments. That'll be on Thursday, June 15th, same time, 1:00 p.m. Eastern. You will see a survey pop up when you log out. Let us know what you think. Let us know how we could make this better, and tell us how great we are. We love to hear that too. No, let us know how we can do better. That's what we really want to know. And thank you everyone for spending time with us today. I know everybody's busy and we appreciate you taking the time to spend with us to learn how to make a better measurement of humidity.